Previous two example, we investigate a simple supported beam with a concentrated load 10 pounds, and we have a shear moment diagram. Both are straight line on the diagram that you see. And what does that mean? If you have no distributed load, both are straight line for shear and moment, each segment of the diagram. If you have a uniform distributed load, then the shear is changed and it will be linearly changed based on the slope equal to the magnitude of the distributed load, 50 pounds per foot. That way it's straight line. And when you talk about the moment, if it's straight line, for the shear, its slope is non-zero. It unlike the example one, slope of the shear equal to zero because it's always horizontal, as you can see there. This one is non-zero. So with that, the moment is a parabola on the moment diagram. So bottom line, as you can see, if the uniform distributed load on certain portion of the beam, then the shear have the change in the slope linearly, and the moment at that segment that have a distributed load, it will be parabola because you take another integral of the linear line, then it become a parabola too. So now let's go to example number 3 with not a simple support, but let's talk about third scenario when we have a cantilever or console. Example 3, if I have, and in this case now we have to deal with the external moment, etc. So we have a beam here and the fixed support to the left, fixed support, and I have a load 10 pounds applied on the right end of the beam, and that beam have a span is this cantilever 25 feet. So from that we need to find out the reactions at the fixed support, and as you can see, if you take moment, take shear, etc. So at that point, as you can see, if you sum up on the force is in x direction equal 0, you don't have the normal force at the fixed support, as you can see. So the horizontal force ax equals 0. If I sum up all the force in y direction, I will have the vertical components of the support, vertical force components, it equal to 10 pounds to make it balance, as you can see. And for the 10 pounds, 25 feet away, so it create the 10 pound on the right, it create 250 foot-pounds clockwise. Then you have something balanced. The reaction here have to be 250 foot-pounds counterclockwise to balance with the 10 pounds on the right, create a 250 pounds for the bending. So for the moment, then you have to, the reaction have to be 250 foot-pounds. So same magnitude but opposite direction have to be counterclockwise. If you are not sure, yes, I suggest you to check moment for x, y, and z components to find out the 3 unknowns at the fixed support. This is statics. Okay, so that's a chance for you to review because very important. If we make it wrong and the support don't know the external reaction at the support, then your diagram will not be shear and moment diagram will not be correct. Keep that in mind. So that stop there for the external because I assume you can be able to figure that out. Let's move on to draw the shear diagram and moment diagram here. So you have the shear diagram and you have a positive, negative, and that is shear, and indicate power gain. And then you also have the moment diagram. It have positive, negative, and you see moment, and that have to be foot-pound, as everyone know. So that is a beam 10 pounds applied on cantilever, 10 pounds applied on the right side. So what we have for the shear diagram, and now you are expert, we can go very fast here. Everyone okay? Start with 0 from the left as always. 10 pounds going up at the fixed support, create a discontinuity on the shear diagram, move up. So it will be 10 pounds, right? Plus 10, everyone see that? And then from left to right, nothing on the beam, no distributed load, no uniform, no distributed load, no concentrated load in the middle. So it keep continue the same straight line. So put it here, otherwise we forget, straight line, uniform. And it finished here at 10 pounds. And then you have 10 pounds going down at the left or at the right side and create a discontinuity in the shear diagram. Move down, exactly the same of that 10 pounds. So it will be from positive 10, move down 10. So it will be close here at 0. So as you can see, draw correctly. Start at 0, finish at 0 from left to right. On way from left to right, by the way. And now for the moment diagram. You have, now if go back to, you have a couple, in this case the moment reactions at the fixed support, 250 foot-pounds. And again, like I say, before you draw diagram, you need to find out what is the external reaction on the support, in this case fixed support, 250 foot-pounds. Go back to the designer side convention for the external load, the couple. If it clockwise, as you can see, clockwise C, then positive cause a discontinuity in internal moment, move up, cause discontinuity in internal moment, okay? And if it clockwise, now our problem, the external reactions at the fixed support is 250 foot-pounds counterclockwise. So it have to be cause a discontinuity in the moment, but in this case, move down, right? Move down. So we start at 0. Then 250 pounds, it had to be moved out, move down here, and that is negative 250, cause a discontinuity in moment diagram. And then 250 from 0 to negative 250 going down, and change in moment from left to right equal to area under the shear curve. You see the shear curve 25 times 10. This one is the area under the shear curve is 250. Everyone see that? 10 times 25 for the length is 250. So the change in moment from left to the right point on that beam have to be equal to 250. In this case, the shear going up positive. So the shear is positive. So it's 250 positive. The area under the shear curve. Positive. Then it 250 positive. From negative 250 for the moment on the left. Plus 250. So it will be 0 on the right side of the cantilever. So you can have the chain and it no distributed load. So it will be straight line. And you can see because the slope V here is horizontal, right? For the shear diagram, horizontal. So it's slope of the V of diagram, the shear diagram equal to 0. Then that one, it had to be also straight line on the moment diagram. And of course, no distributed load, no uniform distributed load. Though it's not parabola as we do on example number 2. Everyone see that. And then you can see here stop at 0. And the 200 pounds here on the right only affect the share diagram, not the moment, unless they couple apply on the right. Make sense, everyone? So that you finish with the share and moment diagram for example 3. So we will have one more example before we practice worksheets A to D.